Okay, I think uh, I think we should just get going. What do you think, Dominique? Are we ready?
Yeah, sure.
Okay, Tian.
Yeah.
All right. Okay. So thanks everyone for joining us for Tian's defense today. I'll just do a short introduction and then he'll give a presentation, and then we'll have an open Q&A for the audience. And then after that, we'll ask the audience to step out of the room, and when we have a closed session with the thesis committee. So Tian joined my group after having done research and education at Peking University, and actually it was in chemistry was his area. And then he did, let's see, what else? He had also done a summer at a research project at Stanford related to, I think it was carbon-based photovoltaics. And in spite of the Stanford experience, he's done really well after coming to MIT. But I actually want to make a point, like that background and you know, the fact that he hadn't even done much computation when he came to MIT really speaks to what is so unique about Tian, and that is his breadth in thinking and creative problem solving, and his ability to find the intersection between fields, like in this research between computer science and materials, in a way that is deeper and more unique than most people that I've ever seen. And so that ability is what Tian has applied to all of the work that he's done in our group. And it has really been very high impact as a result. Just to give you an example, his work on CGCNN, which he'll share with you, this year, it was published in 2018, and this year alone, it's set to, I think, have over 200 citations. So it's really out there making a very big impact. And that's a result of the depth and breadth that Tian brings to his work. And I should point out, he also, you know, along the same lines, he also, you know, this is 5 years, but he managed to fit a very high impact research in his PhD, as well as 2 internships, both at DeepMind and at Google X, where he was, and I know because I've talked to people at both those places, he was equally impressive in those environments and impactful. And so the only other thing I'll say is that it's just been, you know, Tian is one of these sort of treasure people who is so easy to work with and so easy to talk to and so helpful. And so he's just kind of openly collaborative and wants to help everyone else in the group and also outside of the group. And so he's also on his own, you know, started and engaged with a number of really exciting collaborations. So that collaborative nature is another thing that's that I think is wonderful about Tian. So anyway, with that, I'll hand it over to him and let him tell you about the work that he's done for his PhD.
Thank you, Jeff, for this very, very nice introduction. And yeah, so thanks everyone for coming today. And I'm really excited to be here to share about something I've been working in the past 5 years. It's about deep learning methods for the design and understanding of solid materials. So I wanted to start this talk today with a very basic, like undergrad level material science question. So why does the 2 carbon allotropes, like the graphite and the diamond, despite they are all made up with carbon atoms, have such different properties? So we all know that graphite is a soft material widely used as solid lubricants and pencils, while diamond is one of the hardest materials in the world, used in cutting, grinding, drilling, and polishing for industrial applications. So, but I think most of this audience would know that this is because that graphite and diamond have different, very different atomic structure. So graphite has this layered structure in which you have a weak bonding between the layers. So this is why each layer is very easy to slide upon each other And this is the reason why this material is so soft. In contrast, diamond form this tetrahedral structure, which forms a very strong network, which is the reason why this material is one of the hardest materials in the world. So I think this example really represents the ways how we material scientists think about designing new materials for specific applications. So we try to understand how does the atomic structure of materials would determine the property of the materials, and then we try to use this knowledge to design new materials for specific applications. So in the case of a graphite, so since we know that actually layered structure is an important structural feature that leads to the softness properties, so we have since then used this knowledge to identify many other layered materials like MOS2 and boron nitride, and they have also been used in many applications that are similar to the graphite. So a more recent example is this discovery of copper oxide-based superconductors, in which in 1986, people identified that this copper oxide layer is an important structural feature that would lead to superconductivity of materials. And this has resulted in the discovery of a large class of copper oxide superconductors, which raised the transition temperature of superconductors from tens of kelvins into more than 100 kelvins. And this is the discovery that won the Nobel Prize. And a more recent example is this perovskite-based solar cells, in which in 2012, people identified that the perovskite is a key structural feature that lead to high solar cell conversion efficiency. And this class of materials has been widely considered as one of the best candidates for the next generation solar cell technology. So I think we can sort of organize this way of thinking into the diagram that I'm showing here in this slide. So basically, we are starting by looking at the structure of the materials and their corresponding properties, and we try to understand the relationship between the structure and properties. For example, in the case of a graphite versus diamond, we identified that the layered structure is a structural feature that would lead to the softness of the material, and then we use this knowledge to discover a large class of similar materials which shares such properties. So by looking at this process, we can actually rethink this process from a data science perspective, in which we can think about the first step as learning a structure property model from the data, and the second step as trying to apply this model into some new to predict the properties of some new materials. From them, you identify those that you are interested in. So I think the advantage of thinking of this problem in this way is that we can potentially use the we can potentially automate the process of this material discovery process, and then we can apply it to some new problems in which the material structure property relations are less well known. And also potentially we could have a more quantitative prediction of materials properties instead of those qualitative prediction of materials properties. So as you would imagine, that one of the biggest challenges that we are facing in automating this process is this part. So how you can understand the relationship between material structure and the property. So we get this knowledge because our intuition that we gained as a material scientist trained in the university. But how can you develop an algorithm that can automatically do that? So to answer this question, let's look at this statement deeper. So you would actually realize that there are two steps that we achieved this conclusion. The first step is that we identify that the layered structure is a key structural feature that distinguishes graphite from the diamond. So only graphite has layered structure while diamond do not. And in the second step, we found that this structure feature actually leads to the softness of the material. So you would imagine that there are many other structure features that also distinguishes graphite from diamond, even though they have nothing to do with the softness of the material. So this is a basic principle of a large class of traditional machine learning models, whose basic idea is basically try to map the material structure X into a list of structure features. Each one of them describe a different aspect of the material structure. And then you try to learn from the data to say, okay, which one of those structure features or which combination of these structure features would help you to predict the property that they are interested in. But you would immediately realize one limitations of these approaches is that you are pre-assuming that the list of structure features you're using could be able to explain the target properties that they are trying to predict. So this is why we can potentially have a second type of a machine learning model, so-called deep learning models, which is basically trying to let the model discover all these features by itself. So you're directly learning a model between the material structure and their properties. So in fact, this type of machine learning models has been pretty successful in the last 10 years in many other fields, including computer vision and natural language processing, and even playing Ghost. So actually, almost all the best models that we are seeing today are coming in those fields are coming from this kind of deep learning models. However, there's a major challenge. So how you can develop a deep learning model that works for all kinds of solid materials with very, very different structures. So this is a problem that I'm trying to solve in the first part of this thesis. In order to solve this question, so the first thing we need to answer is about how you can find a unified representation for all types of solid material structures. As many of you would know that there are many different types of solid materials, including inorganic materials, solid amorphous materials like glasses and polymers, and low-dimensional materials like carbon nanotubes and graphite. So they have very, very different structure, but how is there any way that we can represent all these different structures in a unified way? So fortunately, we have already solved this problem in atomic simulations, in which we represent all these materials as basically n atoms in the 3D space in a periodic box. So you would imagine it's very straightforward to represent the inorganic material in this way because they're intrinsically periodic. But for non-periodic amorphous materials, what we usually do is to approximate it with a very large periodic box in which you have the aperiodic amorphous structure in it. And for low-dimensional materials, what we usually do is to add a large vacuum space, for example, between the two layers of the two-dimensional materials, so that these two layers will not interact with each other. So therefore, we're approximating the properties of low-dimensional materials. So mathematically, you can think about this representation as a list of three matrices. So the first matrix is a list of integers representing the atom type of these n atoms, and the second is basically a list of coordinates of each one of these elements, and the last one is the periodic box for this material. So after we have had this kind of a unified representation for all solid materials, the next problem we need to solve is really to design a deep learning model that can map an arbitrary material in this input space into the output space. There's no, because this material structure is such a different data type compared with many existing data types that's out there. So there's no existing deep learning algorithm that can work for this problem. So we need to design a new neural network for this type of problems. So there are a couple of challenges that we need to solve. The first one is that how you can capture both the continuous and discrete parts of the solid materials. So for example, what a type of atom you have and the number of atom you have in the system is a discrete value component, while the position of each atom is a continuous component. So you need to capture both of them. And also, we hope the neural network would be invariant to certain symmetries of the materials. For example, you would hope it to be invariant to the permutation of the same atoms, because we know by exchanging, say, two carbon atoms, the materials will not change. Also, we hope the method to be invariant to the choice of a periodic box. And we hope that the method would be able to extrapolate into real elements that do not exist very often in your data set. So to solve this problem, we developed this framework, which we call crystal graph convolution neural networks, which basically try to map an arbitrary material structure into a output materials properties. So here I'm going to give an overview about this method without answering in detail how did we solve the 4 problems I mentioned before. But if you're interested in the details, feel free to ask questions in the Q&A session. So the big picture looks like this. So basically, the framework has 2 components. The first component is a graph construction part, in which you are trying to map the material structure into a graph representation. So the function here is basically to sort of map the continuous part of this problem, basically the distance between the atoms, into a discrete object, the graph representation. So in this graph, each node represents an atom in this material, and each edge represents a bond between the atoms. And so a special thing about this graph is that you have to allow this kind of a multiple edges between the 2 nodes. So this is because of the periodicity of the materials. So for example, if you look at these 2 atoms, they are connected here within the periodic box, but there's a periodic image of this atom in here, which also connects to this atom. So there are 2 bonds between these 2 atoms. So this is why you have to allow this kind of a multiple bonds between the nodes. So the second part of this framework is a graph convolution neural network part, which is trying to map the graph representation of the material into the targeted properties in a way that incorporates the symmetries that I have just described. So after having the graph representation, we put that we do a graph convolution operation, which is basically letting each node to communicate with its neighbors, so that the information can be propagated along this graph structure. And after several graph convolutions, each node would be able to know something about its surrounding environment. And then you have a pooling layer, which tries to pull all this information together to get an overall representation of the material, and then you're using this information to predict the material's properties that you are interested in. So one major challenge, so this basically is how this method works, but one major challenge in this process is about how you can define bounds or edges in the graph representation of the material, because we all know that it is intrinsically difficult to define whether or not 2 atoms are bonded in a general solid state material. For example, you can have very complex inorganic material structures, but also, for example, in polymers, you can have strong bonds and weak bonds coexisting in the same material. So this is a fundamentally ambiguous problem. But so how can you define bonds in the graph representation of the materials? So the way that we solved it is that we actually over-parameterized the graph. We connected more bonds than needed. However, in the graph convolution part, we try to learn a gate, which is a number between 0 and 1 for each bound, so that if this gate value is close to 1, it means this bound is important. And if this gate value is close to 0, it means the bound is important. Basically, we're letting the network automatically discover whether or not which bonds are important. And this turns out to be a very important the part in terms of the performance of the model. So to test how good the model actually performs, we use it to predict the formation energy of inorganic materials. So here we're using a data set of a materials project, which is one of the largest computational inorganic materials data set that is out there. It includes 40,000 inorganic materials covering almost all elements in the periodic table. So because this data set includes such a different wide range of inorganic materials, traditional structural feature-based methods do not work very well on this data set. So we tested the performance of our model on this data set. So in this diagram, we are showing the prediction performance on testing data sets. So the y-axis here represents the mean average error with respect to the density functional theory computed formation energy. So we're trained on DFT results. So even though in principle we can get to 0 error in this diagram, but we all know that the DFT itself has errors compared with experiments. So going to 0 error here doesn't actually have any much realistic meaning. So this error is actually represented in this gray area here. So here I'm showing the result of a 2 CGC network one with the gated architecture, one without the gated architecture. So as you can see that the one with gated architecture had a much better performance compared with the one without the gated architecture. And we are achieving an error that is lower than the error of DFT compared with experiments when you have around 10 to the order of fourth number of training data. So what it means is that our method would be able to reproduce DFT results on testing data, but we can run like 3 or 4 orders of magnitude faster than those DFT calculations. And also because our method eventually achieved a much better performance than DFT, that means that it has the potential for more accurate quantum simulation approaches that is much more expensive than DFT. So we further validated the generalizability of these approaches. So by testing this method on various different type of materials properties. So in this table, we show the performance of our model on a bunch of properties, including formation energy, electronic properties like band gaps, and the mechanical properties like the bulk modulus. And also we're doing a classification task trying to predict whether or not a material is a semiconductor or a metal. So across all these properties, we have shown that basically as long as you have around 10 to the order of fourth number of training data, you are achieving the performance of a DFT with respect to the experiments. And also we're testing our model on various different type of material structures, including inorganic materials, liquid and amorphous materials, crystalline polymers, and the surfaces. So they have shown that they work well for all these different problems. So I think this really shows the advantage of deep learning models compared with traditional structured feature-based models. So that it is basically the general applicability of deep learning models by trying to discover all these structured features by itself. So now let's look at how you can use this method, how you can use these kind of deep learning models to solve a realistic materials design problems. In here, we're trying to design the electrolyte material for the lithium-ion batteries. So many of you would know that one major limitations of the current lithium-ion battery technology is its a relatively low power density. So this is why your Tesla cars can only run 300 miles instead of 1,000 miles. So one way that people think about that you can improve the power density is to replace the cathode material here. Currently it is graphite. You can potentially replace it with lithium metal, which significantly reduces the size. However, it also causes a major problem, which is that you are making this interface very unstable. It will form something called the dendrites, and it's something that will make the battery to explode. So a potential way that you can suppress the formation of the dendrites is to replace the electrolyte materials here so that you can stabilize this surface. And this is what we're trying to do. So we collaborated with a group from CMU where they, in their previous work, they developed this equation trying to compute the stability parameter for this interface. And the input of this equation is basically the shear and the bulk modulus of the electrolyte material, and the output is the stability parameter, in which the lower the value is, it means the interface is more stable. So remember that we actually predicted those properties very well. So this is why we collaborated with them. So by training on around 3,000 open materials data, our model was able to predict the dendrite stability of around 13,000 lithium-containing solid materials. So from which we actually was able to make some recommendations for future experimental verification. So I wanted to note that because here we're training on open materials data, we actually did not do any computation ourselves. So this is why this work is actually super fast. We just did all the work in just 1 week, which you would imagine if you're doing this computationally, it would take at least half a year for this type of project. So this really shows the advantage of this kind of machine learning models for accelerating materials discovery. So now let's go to the second part of this talk. So in the first part of this talk, we developed this general deep learning model to learn the relationship between the material structure and their properties. But as a material scientist, we're usually not only interested in predicting materials properties, but we're also interested in understanding why. So for example, we would prefer to know that it's the layered structure that leads to the softness of the graphite, rather than just having a black box model that telling you, okay, which material is soft and which material is hard. So this is what we're trying to do in the second part of this talk, trying to interpret how you can get insights from this type of deep learning models. So to solve this problem, we are actually looking at each layers of this neural network to get its physical meanings. So because there's a very good correspondence in terms of the graph structure and the original structure, so each layer do have some of the physical meanings. For example, the first layer actually corresponds to a feature that is associated with each element in the periodic table. So because each node is represented by what element they are. But after several graph convolution operations, because each node is talking with its neighbors, so that you then get a feature representation for the local structure associated with each atom. So to make the physical meaning a little bit stronger, we change the pooling function here. So here we're trying to map this feature vector for each local structure into a single value, a scalar number. So this scalar number doesn't mean anything here, but we're adding the constraint so that the average of this scalar number is equals to the average total energy of the materials. So that basically we're hoping the model would be able to infer the local energy of each atom from the total energy of the materials. So we're testing this idea in this data set in which you have 10 to the order of 4th number of perovskites. So in this structure, so site A, site B can be anything from can be any metal from the periodic table, while site C can be any non-metals from these 4 elements. And so the task is to predict the stability formation energy of the perovskites, but we really hope to get insights that is beyond just predicting properties. So for example, for the first layer, we're interested in, we're looking at the element features for each material. And in the last layer, we're looking at the energy, local energy of each individual atoms. So now let's look at the element representations that you learned from the model. So in here, we're doing a PCA that projects the original 64-dimensional feature vector into 2 dimensions so that we can visualize that in this graph. So as you can see that in this graph, all the similar elements are clustered together, like all the alkali metals here, the alkali earth metals here, and then all the transition metals in this area. So this really means that the model is actually learning something that would be able to find the similarity between all these elements. So however, the axis in this diagram doesn't have any physical meaning here. But how do we know that if this model is learning, if this elementary representation actually corresponds to some of the properties that we already know about the element? So therefore, in this plot, we try to use the feature representation learned to predict some of the element properties that we already know, like the block number, group number, radius of the element, and the electronegativity. So the orange bar represents the prediction accuracy of the representation before the training, and the blue bar represents the prediction accuracy of the representation after the training. So as you can see that after training, the performance gets much better. It means that the model is really learning something that is corresponding to these element properties that we are interested in. So in this part, we're trying to extract the local energy of each element, of each atom from the total energy of the material. So I'm summarizing all the results here in these 2 periodic tables, in which the color of each element corresponding to how stable it will be to put this element on the specific sites of the perovskite structure. So the darker the color is, it means the site is more stable, and the lighter the color is, it means the site is more unstable. So for example, for site A, which have 12 coordinations, it is most stable if you have something that is sort of a large and have high electric charge. So in contrast, for site B, it is because it have only 6 coordinations, it is more stable if you have something that is medium sized in these transition metals. but it is unstable if something that is either too large or too small. So these are all consistent with our prior understanding of the perovskite material. And you would imagine that we can apply this approach to some of the less well-studied material structures so that we can understand how you can design a more stable material. So this concludes the second part of this talk. Now let's go to the third part of this talk. So in the first two parts of this talk, we're based on the assumption that we already know both the material structure and their properties. We're trying to learn some relations from it. But what if you only know the material structure without knowing the corresponding properties? So can you still learn something from this type of data? So this is the type of problem we're trying to solve in the third part of this talk. So let me try to motivate this problem a little bit further by giving this example. So the atomic structure you are seeing here represents one of the best performing polymer electrolytes for the lithium-ion batteries. So it's a mixture of this polymer train of PO and the salt, lithium TFSI. So as you can see that this is a very complex amorphous structure material in which it's very hard to study. So for example, what are the solvation structure of the lithium ions and what are some of the dynamical processes that it is going through. But these are important information that we hope to understand in order to design a better lithium-ion batteries. So this represents a case when you only know the material structure of the material, however, you don't have any corresponding properties that you can actually learn from. So how can we? So the key question we're trying to solve here is, okay, if you know a molecular dynamic simulation, MD simulation of this type of systems, how you can identify first, how you can identify some of the key solvation structures of the lithium ions, and how you can understand how these key solvation structures are evolved as a function of time. So the key question we need to solve is that how you can learn for these systems, because now you don't have any properties that you can train on. So what you are trying to optimize. So we're getting inspirations from a very different field, the field of protein folding, in which they have somehow a similar problem. So in protein folding, you are interested in the folding of protein molecules, which includes 3 or 4 orders of magnitude, 10 to the order of 4, 10 to the order of 5th number of atoms. So in which it's kind of hard to know what the folding actually is in terms of coordinates of this many atoms. So one key insight from this this community is that the folding is actually the slowest process in the system, which corresponding to the largest energy barrier in the free energy landscape. So what it means is that we can actually understand the protein folding structure and dynamics just by looking at one or several of the slowest process of the system. Therefore, you can identify these key structures and dynamical processes in the automated learning system. So we try to apply this idea into the material system that we're interested in, but we identified there's a major difference between proteins and the solid state materials, which is the difference between the global and the local dynamics. So let me illustrate what it means by using this toy example. So here you are seeing a lithium atom that is moving inside a FCC lattice. So many of you would know that in FCC lattice, you have 4 octahedral sites and 8 tetrahedral sites. So the lithium ions sort of hopping around between these 12 different sites. So if each site has a slightly different energy. So if you're treating that as a large protein molecule, you're actually looking at the global dynamics of the system, which corresponds to a 12 by 12 transition matrix. And the slowness process of the system is a transition between one octahedral site to another octahedral site. So however, if you're looking at the local dynamics of the system, you can significantly simplify the problem. Basically, the system is basically a transition of one octahedral site to a tetrahedral site, described by 2 by 2 transition matrix. So the key point here is that actually the problem of learning the dynamics of individual atoms can be significantly simplified by learning the local dynamics, and this is even necessary if you are trying to study a more realistic and complex material systems. So this motivated us to develop this graph dynamical networks framework, which trying to do this automatically from the data. So basically, when you have a time series data like the molecular dynamic simulation trajectories, you can consider that as a Markov process in which you have this function map f that maps the current material structure in the current time step into the material structure in the next time step. So there's a theory in the protein folding community which states that if this is true, then we can always find a mapping function that maps this complex material structure into a hidden space in which the complex nonlinear dynamics in F can be represented by a low-dimensional linear transition matrix K. And the dimensionality of this transition matrix K is determined by how many slow processes you have in the system. So the most difficult part in this process is to find this mapping function chi, which we try to approximate it with a with a graph convolutional neural network model that we have just described before. This is basically trying to map the local structure of the lithium ions into a list of states. So this framework basically looks like this. So here, these two graphs represents atomic structure of the materials we're interested in, and the red dots represents the target atoms, like the lithium ions in the system. And so by putting all these structures into the same graph convolutional neural net model, we're learning a representation for each atom that we're interested in. And then we're putting that into a VAMP loss function, a loss function that is developed by the protein folding community, which tries to optimize this equation. So basically, from this method, we're learning two things. The first thing is this mapping function chi, which tells you what are the dynamically most important local structures in the system, and also a transition matrix K, which tells you the detailed dynamical processes in the system. So we tested this idea in this two-way system of lithium ion hopping in the FCC lattice. So we have successfully identified this transition between a octahedral site represented by the red dots here and a tetrahedral site represented by the blue dots here, and we correctly identified the transition timescale for this transition. So, and also we compared that if you're not using our model, you're using a normal neural network, you are getting the raw and the global dynamics of the system with a very, very different time scale. And also we have shown that the model we learned would be able to correctly predict the dynamics of the lithium ions in some new testing trajectories, as you can see in these two curves here. And also because this is a relatively simple system, we can actually reconstruct global dynamics of the system, the 12 by 12 transition matrix from the local dynamics that you learned from the model, reproducing the relaxation timescale associated with it. So now let's look at how we can apply this method into solving the original problem that we proposed at the beginning. So by learning from the molecular dynamic simulation data for the PU TFSI system, we immediately identified 4 most important solvation structures for the lithium ions. So the reason that it is 4 is because the transition between these 4 states are much slower than any other transitions of the materials. So the state 0 is corresponding to a lithium ion that is partly coordinated by the polymer train and partly coordinated by the salt. And the state 1 is very close to state 0. The only difference is that you have this AND group here that is connecting with the lithium ion. So the state 2 is a lithium ion that is fully coordinated by the TFSI salt. And the state 3 is a lithium ion that is fully coordinated by the polymer train. So it's kind of because we're already learning this from without any supervision. So it's kind of it's even kind of a surprise that we can understand the physical meaning of each one of these states. So after knowing this information, you can immediately get some insights. So for example, if you compute the charge associated with each one of these states, you would know that the majority of states, state 1, state 0, accounting 70% of the lithium ions, carries very little charge. So this means that they're not contributing much to the lithium ion charge transport. And this is one of the major reasons why these materials have relatively low conductivity. And it is the reason why it hasn't been commercially usable. And so you can go a little bit further, and by looking at the 4x4 transition matrix we learned from the model. So in this diagram, we're showing that how each one of these transitions are contributing to the overall charge transport of the lithium ions. So you can see that the most important species here is actually this state, which is a negatively charged species, which is kind of surprising because the lithium ion is positively charged. So it's kind of surprising that a negatively charged species is the most important species contributing to the charge transport. And this is recently observed in experiments, and we're providing an atomic scale explanation to this problem. So now let's, so then you can also go a little bit even further, that you can actually do an eigenvalue decomposition of this transition matrix K, which basically gives you these eigenvectors. This tells you what are the specific atomic scale movement associated with each one of these transitions. For example, we know that this 3.6 nanosecond transition corresponds to a lithium ion transporting between a PEO coordinate site and a lithium TFSI coordinate site. So these are all some of the information that is very hard to get with traditional approaches. And we're learning that from machine learning model. And so we're still hoping to get some experimental verification for this result discovered by the machine learning models. So now let's go to the final part of this talk. So in the first three parts of this talk, we're based on the assumption that we have some existing data of this material system. But what you are studying with nothing, how you can explore a new material space without any initial data to begin with. So how you can explore this space in the most efficient fashion. So this is the problem we're trying to solve in the last section. So the motivation of this problem is that we're really trying to design a better polymer electrolyte system. As I mentioned before, that the conductivity of this material isn't high enough to be commercially usable. So to potentially improve the conductivity, you have two things you can change. One is the type of polymer you are using. The other is the type of salt you are using. So the key question we're trying to solve is about how you can increase the conductivity of the lithium ions in these systems. So however, the original system is too complicated. Here we're looking at a coarse-grained representation of this polymer electrolyte system. So what it means is that instead of looking at their specific atomic structures, we're basically treating, we are basically treating all these ions as a charged particle with certain radius without looking at their specific atomic scale with atomic structure. And also, instead of looking at the atomic structure of the polymer, we're just treating them as a bunch of neutral beams on a string. So the way that you are matching these coarse-grained representation with the original material structure is that you are trying to match the interaction strengths between these species in corresponding to the original chemical structure. So the goal really is about trying to find the best polymer electrolyte in this coarse-grained representation of the materials. So in this work we did three things. We try to change the anion of the system. We try to change the secondary site in the polymers, and also we try to change the polymer train. So in this talk I'm going to focusing on the first part. So you can imagine that if you're trying to change the anion in the system, there are 5 parameters you can change. First is how strongly this anion is interacting, with the counter anion, and how strongly it is interacting with itself, and what is the radius of the anion, and how strongly it is interacting with the polymer train, and what is the concentration of this salt. So after knowing these 5 parameters, you can, so we are constructing a coarse-grained system, and then we are running a coarse-grained molecular dynamics simulation from which we can get the lithium ion conductivity of the systems. So however, even though this is a coarse-grained simplified representation of the system, exploring this high-dimensional space is still extremely expensive. So assuming that you are only looking at 7 data points in each one of these dimensions, you are looking at more than 10,000 simulations, which is too expensive to run. So the problem, so therefore the problem we're trying to solve is basically really how you can explore this high dimensional space in the most efficient fashion. So in here, we employ a method called Bayesian optimization, which I'll illustrate in this diagram. So at the beginning, you don't have any data. So you just randomly sample in this high dimensional coarse grained space and several axes, and then you run a CGMD simulation and you get the data of its corresponding conductivity, and then you use the data to train a Bayesian optimization model, which basically predicts the Y based on X. So this is exactly the same as what we have been doing before, but the special thing about this type of model is that you can use the Bayesian rule to actually invert the probability distribution so that you can actually have a probability distribution of the X. So using this information, so in the next iteration, you can look at what is the best and optimum positions that you want to explore in this high dimensional space. So those optimum positions will be either those positions that is most likely to have a high conductivity, or the regions that have the highest uncertainty. So by doing this over and over again, we can actually have a very efficient way to explore this high dimensional space. So I'm summarizing the result here in this diagram, which basically shows, so the y-axis represents the best materials we have found up to this point, compared with the original system, the lithium TFS SIPO system. And so at the beginning, at the first 50 simulations, we're doing this exploration via random search. So however, after 50 simulations, we switch into the Bayesian optimization. So you can see that you immediately get a much better performance compared with random search. And so we actually found the global optimum with just around 110 simulations, which is less than 1% of the numbers that we saw in the last slide. And also, just like many machine learning models, you can try to get some insights from these Bayesian optimization models. For example, you can know how important each parameter is contributing to the conductivity. For example, here we know that the radius of the anion is the most important contributing factor. And also, you can get these plots will basically tell you that what is the optimum interaction parameters that would give you the highest conductivity. For example, here it tells you that what is the optimum radius of the anions and what is the optimal interaction strength with the polymers. So one major limitations of this work is actually we're still operating on this coarse-grained space, which is a continuous space in terms of the way that the interaction strength parameters can be tuned. However, we should know that actually the real chemical species is a discrete space. It means that it is not all points in this high dimensional space actually corresponds to a real chemical species. So therefore, the next challenge that we need to solve is basically about how you can decode material structures from this interaction strength space so that you can design a real chemical structure for this polymer system. So this basically concludes today's talk, in which I have presented a series of deep learning models that are trying to solve various different type of problems in material science about designing new materials and understanding scientific insights from data. So more specifically, we developed a deep learning model, the first deep learning model for solid state materials that learns the relationship between material structure and properties. And we explored how you can extract scientific insights from the model in a way that can be understood by the material scientist. And also we explored how you can learn models without any properties. We successfully learned the local structure, the key structures and dynamical processes from a time series molecular dynamics simulations. And finally, we explored how you can search a material space without any initial data in the most efficient fashion by employing some methods in the Bayesian optimization approaches. So yeah, this basically concludes my talk. And in the acknowledgement section, I would like to first thank my advisor, Professor Jeffrey Grossman, for being such a great advisor, not only academically, but in nearly all aspects of my graduate life. He has always been supporting me to look at big problems. He has been guiding me about how you can look for this kind of big problems and try to design new algorithms that can solve it in a different way that we are previous doing in the material science, in the material science. And also, I learned a lot from him in this way of thinking about how you can design projects in a way that have the highest impact. I also would like to thank all the collaborators in my group, including Dr. Arthur Franz Arnold, Dr. Yamin Wang, Dr. Huashan Li, and Dr. Taishan Zhu and Shen Gong. And also, I would like to thank all the members of the Grossman group. And this is such a great group with very nice group culture. And I would imagine my graduate life to be very, very different without all the scientific discussions we have and many, many other activities that we are doing in this group. Also, I would like to thank all my collaborators and the members of my thesis committee, including Professor Yang Xiaohong, Professor Rafael Gomez-Bombarali, Professor Jeremiah Johnson, Professor Adam Willard, Professor Elsa Olivetti, Professor Julie, and Professor Venkat Viswanathan. So I really learned a lot through all the discussions with them, and by collaborating with them, I learned how you can work with researchers from many different fields. So finally, I would like to thank my parents who have been extremely supportive of my study here at MIT. So one fun fact about this photo is that actually my parents was able to travel all around China and many parts of the world with the dog in my family, Dodo, since I studied my PhD. And so, I really hope in the future I would be able to spend more time with them and also traveling with them. Also, I would like to thank all my friends that I have been able to know at MIT. And this is a picture where we're celebrating the Chinese New Year last year. And yeah, I think all the activities we're doing with these friends are a very important part of my graduate life. And I feel very fortunate to be able to know all of you. So this basically concludes this talk, and thank you very much for your listening, and I'm happy to answer any questions. Thanks.
Right. Thank you, Tian. Oh boy. Feedback. Maybe if everyone their mic. Okay. Oh, that's better. Okay. Thanks, whoever did that. So Tian, thank you. That was outstanding presentation. And now we can open the floor up to questions. You can, if you have a question, since I can't see everyone on the screen, please raise your blue virtual hand and I'll call on you.
Okay, I'll start.
Ahead, sure.
So very interesting, impressive set of works, Tian. So you showed the PCA analysis of the different elements in a two-dimensional space. So I wonder what is it? So what were you learning from? So this 64 is, I guess, 64 elements. But then how big is the vector space that you're looking at?
So just to clarify that 64 is the dimension of the hidden feature space. So the number of features that we're learning for each element. So in total we have all the elements in the periodic table, and for each element we are representing it with a 64-dimensional vector, and then this information sort of used in the machine learning model to sort of learn the property, learn the formation energy for all the perovskites. And so after the learning, basically you will get a feature for each element in the periodic table, which is a 6 4-dimensional vector. So, and in here, we're projecting that into 2 dimensions. Then this is the result.
So, can you give some examples of these 64 atomic properties? So these are electronegativity. So are they atomic properties? Are they perovskite specific properties?
Oh yeah. So yeah, sorry, I didn't clarify that. Basically, so original. So this feature is sort of at the beginning, it's a randomly initialized number. It's basically a randomly initialized 6 4-dimensional vector for each one of these elements. But during the training, you are sort of optimizing this feature for each one of the elements in a way that you are trying to predict the target property, the formation energy. So basically, so this orange blob corresponding to sort of the initial sort of a randomly initialized feature for each one of the elements, and this represents the sort of the value that the feature you learned after the training. So here we're basically trying to test how you can learn from scratch. So if you don't give the model any information, can the model learn something about these elements just by predicting formation energy based on the atomic structure? And so it's kind of interesting that it does learn something that is coarse, that we can actually understand. Yeah.
If I can keep, so I understand that you can learn by doing back propagation on the waves. So are these 64 numbers for each element? Are they kind of weight that you propagate?
Yeah, these are the weights in the model, and these are randomly initialized.
Thank you. And when you do the PCA, it is kind of a linear model. So I mean, I guess if you have a cross-validation accuracy of 70–80%, I guess you can still improve on it. So any idea of are you satisfied with this, or do you think you can still get better with?
Yeah. I think we can get these results based on this data set. So this data set is basically a bunch of perovskites and their energies. So I think this is probably the best result we can get for this system, where we can potentially improve it a little bit, but not that much. However, if you have a different data set, which is richer than those perovskites, for example, all the inorganic materials in the materials database, potentially we can do something better. Yeah, this is my thought.
Thank you.
Thank you.
Okay. Oh, we have a question from, but it's HY, and I don't see a picture, and I don't know who's HY. But go ahead, HY.
Oh, hi. Sorry, I'm Hongzhou. So I'm one of the friends of Tian, okay. And it's I'm very happy to see all the achievement Tian's made, and this is a very impressive talk. So first, I would like to ask a sort of follow-up question of Professor Judy's. So in this project, you claim that you learned local representation for the energy of perovskite. And I think, yeah, in the next slide, you show that so I'm kind of interested in how you make this plot, because the local energy would be a function of the local environment of the specific atoms, right? So it depends on the neighboring atoms of the specific atom you are looking at. So how can you make such a plot?
Yeah. So this is a good question. I didn't explain the details, but basically this is the average energy of putting these elements in this site across all different local structures that you have in the data set. So this is the average.
It does depend on the local structure. I mean the environment, right? But
yeah, it does.
The trend is very stable.
Yeah, there's certain standard deviation across different local structures, but yes, the trend is stable, and yeah.
Okay, yeah, that's very interesting, because this kind of energy decomposition is also a very interesting topic in quantum chemistry. And actually, there is no unique way you can like decompose this energy because in an interacting system, you just don't have a well-defined way. You just don't have a well-defined like atomic energy simply because they are interacting. So it depends on how you like divide the interaction energy like onto different atoms. But it's very interesting to see that you can learn such a chemically intuitive trend about those atoms. And my second question is about like page 13.
13, right?
Yeah, 1-3.
Okay.
Yeah, so you show like the MAE of model and DFT. So just to check my understanding, the MAE submodel is to train your CGCNN model like directly against experimental data, right?
No, it's against the DFT, and so this is the error with respect to DFT.
Then what is the DFT MAE DFT?
So
what
MAE
is that
DFT
error?
is the error of DFT with respect to the experiments. So I think,
okay.
Yeah, we're comparing this number because so in principle you can go to 0 here, but my thought is basically it doesn't make much sense if you go to 0 here, given that you have errors in here.
I see.
Yeah, that is the thinking. Yeah.
Okay, so yeah, at first I thought you're claiming that when the model is trained like against experimental data, it can outperform like DFT. But do you think that's possible?
Yeah, that is yes, that is actually possible. And yeah, I was doing there's a recent work basically showing that by training experimental data, it is possible to get a prediction error that is better than the error between DFT and experiments. Yeah, but of course you need to make some sort of a grain of salt in terms of these errors because basically the testing materials shouldn't be so different from the training materials. Unlike DFT, you can potentially have very different materials compared.
So it's still the transferability problem.
Exactly, but yes, it's possible that there are empirical evidence showing that you can get better accuracy than DFT with respect to experiments by doing so.
Okay, that makes sense. So that leads to my last question. So you presented that your method is so flexible and can do a lot of like interesting things. So what do you think is the like biggest challenge of this kind of method or like machine data-driven model in general?
Yes, that is a great question. So yeah, I don't have so I only have my own thoughts. But so first, there are two parts. One is methodology. The second is data. So in terms of methodology, so yeah, I do show that the method actually works very well across different materials. But I believe there's something that the model, for example, is not very much capturing. It's basically it's basically very long-term interactions like the Coulombic interactions. So in here we're trying to capture long-term interactions by sort of propagating information in this graph representation of the materials. However, if you're looking at the interactions that is sort of across, say, 100 periodic cells, so those interactions will never be captured with this method. But some of those information could be important to some of the properties we're interested in. So this is basically a problem of basically how you can describe charged particles and their interactions in this kind of machine learning based force field. And this is still an unsolved problem. And and the second thing really I think is about the data. It's about how you can have a really unified data for all different kinds of materials, and you can somehow assemble them together so that you can have a much more powerful machine learning models than we have today. So I think it's going to be a community effort for us to building up this kind of shared data infrastructure that can have data from many different fields together.
Okay,
so thank you so much.
So thanks for the questions, and we have another blue hand up, Graham.
Hey Tian, that was an amazing talk. Clearly you've been really busy the past couple of years. I just had a really quick question about, I wanted you to expand on something you talked about in the fourth part of your talk, where you were talking about the CGMD results for trying to map the continuous space of the different pairwise interactions. So you kind of alluded to this a little bit near the end, but I was just hoping you to expand a little bit. So you mentioned the challenges to get from this continuous space back to discrete chemistries that kind of fill within that space. Can you just expand a little bit more on like that process and kind of how to know whether a predicted space is actually like possible with real chemistry?
Yeah, this is a great question. So I think I don't have a sort of the perfect solution to this problem, but my thought is following basically. So first is that we need to have more materials in this space. So basically, if we try to get basically data about all these different sorts, then we can try to actually populate this space. From this, we would know, for example, in which positions in this space is denser compared with others. From this, we can potentially get a probability distribution of the chemical structures by sort of bridging this discrete space into more concrete space, into a continuous space. Then we needed to have a algorithm that would be able to invert that, which is some way kind of a challenging, but there is potentially some solution that we can think about that can solve this problem. But yeah, it's overall a challenging problem to sort of in a general sense to sort of decode an inorganic material structure. However, in a more constrained case, there is some solutions to this problem.
Thank you. And do you think it's also possible to use this as a design descriptor for discovering new salts? So as a way of kind of screening new salt candidates?
Yeah, I totally think that is possible. And I think that is going to be a very exciting direction to go forward. Yeah.
Awesome. Thank you so much.
Thanks for the question, Graham. And Professor Olivetti has her hand up.
Can't unmute here. Can you hear me?
Yes, I can hear you.
Great. I just wanted to follow up. I was going to ask you the same thing that Graham did, but a follow up on that. The process that you just described, or the way you answered that, seemed like a pretty data intensive approach. Are there ways that we could leverage kind of the grammar or sort of the structure of what materials we expect to try to, do a little bit of, I guess, machine learning on the machine learning to sort of augment data sets? Are there ways that you think that could help alleviate some of the data intensity of what you just described?
Yeah, totally. So I think it is harder for the salt to, so really that's the big problem, because I think so in this bigger team that we're working on this problem, we actually collect from literature. So, and in total, I think we get 20-30 salts in total that people have studied up to this point in terms of salt. You would imagine that's not a huge number in terms of salt, but then the question is about how you can design these anions. That can be an interesting topic which we can think about. Okay, for example, how people design new ions, right? So can you leverage some of the other information that we know about these anions? So that is a question that these are some of the potential other information that we can leverage. And in terms of polymers, I think there's more solution to this problem in which we have a little bit more data for polymers. We can leverage some of the data from the molecules, and there are also some data about polymers. And this is exactly what I'm trying to working on, what I'm working on currently, and to trying to tackle this problem.
Great, thank you.
Okay, thanks for the question. Any other questions from the audience before we move to the closed session? No questions. This is it, guys. This is your last chance to give them a hard time, or well, maybe for now. Okay. Well, we will have a lot more questions in our closed session with your committee. So at this point, let's all thank Tian again for the presentation. and then I'll ask everyone but the committee to please leave the room. So a big round of virtual applause for Tian one more time. So, all right. Awesome. Thanks everyone for coming, and thanks for also leaving, unless you are a committee member, as we move now to the closed session. Great.
Okay, so I'm now moving all of the committee members and Tian into the next room.
Oh, did I do that wrong? Was everyone